Want a government examine. Okay, first we're going to do electrostatics, and then we're going to do electric circuits. And then, if time permits, we're going to do electricity and magnetism. We could do a whole course on electricity and magnetism. We could do 3 years of physics on electricity and magnetism, but something's got to get sacrificed here. What are you looking for? Justin? So what does this word look like? Does it look kind of electrical? Kind of staticky? What is it? First, we're going to look at forces that little things can make as far as their charges go. So two charges, they have a force of either attraction, if what? Yeah, positive and a negative, right? Or there's two examples for repulsion. Yeah, if they have a like charge, they're going to repel. Nothing new here, right? There's a formula that'll tell us and measure this. That's it. That is the force. This is some constant, 9 times 10 to the 9. Now if you want the units, there they are. That's force, newtons. M, what does that stand for again? Meters, yeah, right? It's a distance. It's over r squared. And c is something else. That's a big C, not a little c. That's not the speed of light. That's the new thing. Coulombs. And R would, well here, let me write also. K is a constant. Q1 is charge on particle 1, or point 1, or whatever. And vice versa. Does this formula look familiar? Where did we use something that kind of looked like that? Yeah. That's a universal law of gravitation. Looks awfully similar, doesn't it? Square of the inverse law, right? The farther apart they get, it's not linear. It's, if r is doubled, we got 1/4 of the force. Same kind of thing. Okay, so that should look kind of familiar. What is a charge? An elementary charge, i.e. that of an electron, which is what kind of charge? Yeah, it's negative, you know that. Okay, E is 1.6 times 10 to the minus 19 coulombs. But if it's an electron, it's negative. And a proton, yep, times 10 to the minus 19 coulombs. Okay? So C is coulombs. And that's our unit for charge. Just like meters is a unit for distance, right? Seconds is a unit for time. C, coulombs, is a unit for charge. The example. So you kind of done this formula before, just not with this type of stuff. What is the force between a proton and an electron in, and I believe I did my research, in calcium, where D is, how far do you think it is between an electron and a proton in a particular atom? Yeah, like on the magnitude of -10 meters. So that's one more than a billionth of a meter, which is pretty darn small, which we would expect. As you can't see it, not with the naked eye. So force is K Q1 Q2 over the distance between them squared. K is 9 times 10 to the 9. Now don't write all the units. As long as you're in meters and coulombs, then force is going to be in newtons. So don't get all messy with it. Just make sure everything is in the appropriate unit. And we don't have to get all confusing. What is Q for a proton? That's our elementary charge. 1.6 times 10 to the minus 19 coulombs. What's that for electron? Same thing, only the charge is negative. The distance between them is 0.8 times 10 to the minus 10. Don't forget to square it. Okay, and just like universal law of gravitation, the rest is just a calculator exercise. 9 to the exponent of 9 times, now are you going to enter this twice? Or are you guys going to be smart and enter it once? And square it? That's what I thought. Squared divided by 0.8 to the exponent of negative 10. Whoop, negative. Squared. And that's the advantage of using the E button on there, not 10 to the, because I don't have to use brackets, right? It'll work. Should be pretty small, right? Yes? Well, I just know the sign's going to be minus, but it's the same number. I can square it. Take the minus and stick it out here. Now it's plus. So minus 3.6 times 10 to the minus 8. Force is in newtons. So what does negative versus positive mean? It's just direction, right? We're just talking about gravity. Is it minus 9.8 or is it plus 9.8? It depends what way you take plus and minus. Minus here implies these forces would be attracted. So I'm taking repelling as a positive, so that way is going to be negative. I can switch it the other way around, whatever, doesn't matter. Okay? That's just direction. So it doesn't really matter about plus or minus here. You know it's going to be a force of attraction. Okay? That's the magnitude, 3.6 times 10 to the minus 8 newtons. Okay? Now, did someone put it in twice and get the same answer? You would, right? Now, what is the net force below on the middle charge? Anyone remember what that funky little mu is? But there's no friction. Micro, yes, good. 1/1,000,000th of a coulomb. Micro. There's a picture of 3 charges. I got a left charge, I got a middle charge, and I've got a right charge. If I don't specify that this is a negative, then you must assume it is a positive. If it makes you happy, put them in there. Don't think we're just going to have one planet here with this formula. We got lots of planets, okay? We've got 2 forces. Now we need some distances. That's 0.6 meters, and that's 0.9 meters. Okay? So again, mu is a micro, which is a millionth, 10 to the minus 6. So common sense. Or maybe it's not. I don't know. What direction is that middle charge going to go? From this force, he wants to go what way? He's going to get repelled from this one, right? From this one, what direction is he going to go? He's going to be attracted. So obviously, this one's going to go to the right. Okay? So when I say net force, sometimes we're going to add these, sometimes we're going to subtract them. Okay? You might not know intuitively what direction this guy is going to go. Don't worry about it. Just figure it out one at a time. Pretend this one isn't there. Do we know how to calculate the force between these 2 charges? Do that. And then pretend he's not there. What's the force for these 2? Do it again. Okay? And then take the net of the 2. Either you're adding, subtracting, but make sure your answer makes sense. If I got an answer going to the left, I did something wrong. Okay? Obviously this guy is going to go that way. Sorry? Well, you can do it any way you like. So, let's look at these. I know the force is K. Q1, 3 times 10 to the minus 6, positive, times 2 times 10 to the minus 6, positive, over the distance squared, which is what? Ba-do, 0.15 newtons. So if you want to take positive as right here, I guess then that one's going right. But I'd suggest maybe don't think that way. Just know that this is a positive. It's going to repel this charge. You know that thing is going to go right. Okay? These 2 charges. Okay? I know F is K. This one times that one. So here, that one's going to be negative, which implies it's left if you want to think that way. But I suggest, like, it doesn't really make sense, does it? Because you know this thing's going to, we're talking about this charge. It's going to go right. It's going to be attracted by that guy. So this comes out as a negative. Does left help here? It doesn't. Okay? I know on the middle charge, this thing's going to attract it. It's also going to be right. So the sign here doesn't make any sense, does it? Does it help you? Just think common sense, okay? They're both right. So am I going to subtract these, add these? Yeah, I'm not even going to worry about this thing, okay? Don't even worry about that in the formula. Just use common sense. That thing's right, that thing's right. So the net force here is that one plus that one, which is 0.194 newtons right. Okay? Make sense? Whoa, shoot. Oh my God, might be 3 questions. It's not, it's 6.